In our first lecture, we're going to talk about how to design indexes for a query's where clause. We're going to build indexes for the where clause. We're going to determine how selectivity really affects key order. And I'm going to show you how to visualize an index's contents, because it's so helpful from How to Think Like the Engine to have the actual index contents in front of you. You're going to be using that likely throughout the day, anytime that you have questions about why is SQL Server using this index or why isn't it. Let's start with a really simple query, a where with just a single equality search. Let's take the users table, and I want to go find all of the people named Alex. Now, when I first get started designing queries like this, they aren't very real world because I don't have an order by in there. I don't have joins to other tables, but I got to teach you how to walk before I teach you how to run. If I ask SQL Server to pull all of the Alexes and the places where they live, let's see if I only have the clustered index of the table, aka the white pages from How to Think Like the Engine. Let's see what our before metrics look like, because indexes should, of course, drop the number of logical reads. Like we talk about in How to Think Like the Engine, you're going to turn on Set Statistics IO on and go check the number of logical reads before. Right now, when I'm doing a clustered index scan on the 2013 database, we're talking about 45,000 8K pages. And if I look at the execution plan before we've added any indexes, Clippy has an idea. I think of these missing index recommendations as like Clippy, the old Microsoft Office assistant, who's like, hey, I see that you're writing a letter to Grandma. Would you like some help with that? And in reality, you weren't writing a letter to Grandma. You were trying to write your resume or a project plan. Clippy got fired from the Office team long ago, Microsoft Office team. He no longer shows up in Word or PowerPoint. Instead, he shows up in SQL Server. This is really written by Clippy. Clippy's like, hey, buddy, I see that you're querying by the display name column. Wouldn't it help if you had an index on the display name column? And he doesn't even look at the fact that we're also asking for location here. Now, I make fun of Clippy all the time. I make fun of Clippy because he's a really easy target to go poke fun at, and I'll talk more about how Clippy's thought process works later in the day. But at the same time, I'm kind of mercifully glad that I get Clippy, because I spend about 50% of my time in Postgres these days, 50% of my time in SQL Server. Postgres doesn't have Clippy. There are a few extensions that you can add on that are maintained by third parties that kind of halfway do this kind of thing. But I'm gloriously happy that Clippy even shows up for work. Clippy, though, only is able to work for a few milliseconds. Clippy's recommendations are a byproduct of building the execution plan. They're not the main point of building an execution plan. SQL Server needs to ship those query plans quickly so that your query can actually run. If you and I put more than a few milliseconds of the time into this, you and I will come up with better recommendations. You and I would probably say, well, we're asking for the Alexes, but we're also trying to find their location. And that's just one column. It's not a very wide column. So what we could do is we could include location in our index. You'll notice that I didn't include ID. Our query is asking for ID, but I didn't put ID down there in the includes. Like we talk about in How to Think Like the Engine, SQL Server will automatically include the clustering keys in our non-clustered indexes. Whatever way our table is organized, SQL Server already automatically takes, in this case ID, and copies it into every non-clustered index. This is part of the reason why designs for clustered index are so important. I don't want to cluster on a whole bunch of columns. I want to cluster on as few as possible because those keys for the table are included in every non-clustered index, whether I ask for them or not. If I do include the IDs manually, if I put ID inside my include columns, there's no extra cost for it. SQL Server's putting it in the includes either way. The time where I'm going to add ID into the includes is if I actually need it in the query output, and I think that it's possible that someone later is going to come in behind me and change the clustering key. If I work in a large team and there are other data modelers who might change the clustered index on a table, then I might include it. Otherwise, I generally don't. So if I create that index, if I create the index on display name, then location, and I turn around and run my query again, I want to see that the index, of course, shows up in the plan. That's step one for me of making sure that it was a success. Step two is checking the number of logical reads. Did my query read less 8K pages? And in this case, it does. It drops from 45,000 logical reads down to just 16 logical reads. I should talk about that for a second, though. There are a lot of ways that you can measure queries. You can measure them by logical reads, you can measure them by CPU time, by duration, all kinds of things. These days, especially the more that I work with Postgres, the more I think that logical reads may not make sense as our main measurement for a query. If I could only pick one measurement for a query, it's probably going to be CPU time in most cases. And the reason that I say CPU time is because up in the cloud, you get billed for that. And I want to start thinking longer term about my career. I want to minimize the costs of my queries long term, because that's what people are generally going to pay you for. However, inside the scope of this class, when we're talking about index tuning, the first place that we start with metrics is logical reads. Just because the less data that you read, the more likely it is that your index strategy is effective. Moving on. So next up, let's make our query a little bit more complicated. Let's add 2 equality searches instead of 1. Let's go find all of the people whose name is Alex and who live in Seattle, Washington. There are a couple of ways that I could index for this. One way would be to index for display name, then location. The other way would be to index by location, then display name. But hold on, hold that thought. Before you start trying to figure out which one of these has more distinct values, let's flash back to the last index that we just created. We just created an index on display name, then included location. So what our query can do is it can seek down into just the Alexes. And it is going to have to read all of the Alexes because they're not sorted by locations. But are there that many Alexes? What if username was unique? If username, like display name, was completely unique, I don't need location in the key at all. Having it in the includes would be completely fine. The more Alexes there are, the more it starts to matter whether that location is in the key or not. But we need to go find out. We need to go run this query with the existing index and see how hard it is to read through all of them, checking their locations. Let's run that query with our existing index that we just created. And 16 logical reads, that's fantastic. People aren't going to arm wrestle you between the difference between 5 and 15 or 10 and 20 logical reads. People just don't notice the difference. If you had this index in place, no one would complain about the performance of this query. Now, it's not a perfect index because if I hover my mouse over that index seek and I look at the pop-up, if I look at the pop-up there, and I'm going to zoom into it to show you a little bit more details. If I look at the pop-up, down here there are a couple of pieces. Microsoft, when they're setting up pop-ups, they tend to, or even just anything on a screen in SQL Server, they tend to organize it in one of two ways. Either they put it alphabetically, which makes no sense for storytelling, or else they have the shoulder-mounted data cannon, and they load up the shoulder-mounted data cannon and they fire it at the screen, and wherever the data happens to land, they're like, screw it, ship it, and so the data ends up scattered all over the place randomly. The first thing that SQL Server's doing in this execution plan is the thing all the way at the bottom, which makes no sense. Down all the way at the bottom, it's saying I am going to seek on display name. Then there's another thing up here that's called just a predicate. It doesn't say seek on it, it just says predicate. And I really wish that it had another word like residual predicate or leftover predicate. What this means when you see an index seek like this with a predicate plus a residual predicate, it means that SQL Server seeked on the first column, but only the first column. The more data that you have in a table, the more this starts to matter. Don't be fooled by something saying index seek on the execution plan. That only means we seeked on the first column. If you have a very generic first column, I'll give you an example, country. There aren't that many countries in the world. And if you were asking for all of the customers in the United States named Brent Ozar, seeking to the United States doesn't mean anything. I want to know whether I'm seeking on every column or whether I'm scanning on some of the columns. To understand what this means out in real world, it helps to visualize the contents of the index. This is exactly how I built the pages for How to Think Like the Engine. What I do is I take the query that created the index and I copy paste that, I write it into a select query. Now, if you just hit execute on a query like this, remember you are bringing out a lot of the data in the tables, larger tables. This can end up being a ton of data, but this is really useful. So here, if my index says, go create an index on display name, just include location, what I'm going to do is I'm going to say, go select from the users where display name equals Alex. That'll show me exactly what SQL Server sees when it seeks in to the Alex. If I want to test that I wrote the right visualization query, here I removed the whereby and I just dumped out all of the users ordered by display name, because in the Stack Overflow 2013 database, it's about 2.5 million rows. It's doable in SSMS, even though it produces a lot of results. If I want to see what that looks like, I can run the query and look at the execution plan, or even just look at the estimated execution plan. What I'm looking for when I build a visualization query to show me the contents of the index, I'm looking for an execution plan that only has this index in it and nothing else. No sorting, for example. If you see a sort in this execution plan, that tells you the SQL Server isn't taking the data out of that index and showing it to you as is. It's doing some kind of morphing on the index. You may have to only use an estimated plan for this if you're just looking at the query plan to check your work, because of course if the table has tens of millions or hundreds of millions or heaven forbid billion rows, it's going to take forever in order to execute that query. You can filter with a where clause in order to get your results faster into SSMS, but to see the data accurately, only use a where clause on the first column of the index. If you use a where on the first column, then your plan's going to be an index seek. If you see any kind of sorts in the execution plan, then you're not truly seeing what's inside the index. So let's try it with ours. Let's create our index. Oh, yeah, let's create our index. Then let's go run our query. Show me the users where display name equals Alex. And if I'm looking at the visualization query to see what's inside the index, oh, my clicker stopped working there. If I'm looking at the query to go see what's inside the index, show me where display name equals Alex, I am only ordering by display name. Because remember, in my index, they're only ordered by display name. They are not ordered by location because I didn't use a location up inside the key. If I look to see what SQL Server sees when it opens up that index, here's what the data looks like inside that index. Sure, I can seek to Alex, but if I'm looking for the ones who live in Seattle, I'm going to have to read more rows than I want trying to find the Seattles because they're not sorted in the order of location. Because of that, if you really wanted the absolute ultimate performance, you probably would want to have location up in the key instead of in the includes. Let's come back to the couple of different ways that we could do that. One way that we could do it is to create the index on display name, then location. The other way that we could do it is to create it on location, then display name. I'm going to create both of those just like I would do in the real world. I know you think I'm crazy there, but I'm talking about a dev server first. I'm going to create both of those indexes. Then I'm going to test them using index hints. I'm going to turn on set statistics IO. I'm going to run the before version of the query when you use index equals 1. Now, I should say I don't like index hints out for production usage. I don't like embedding index hints inside query code, and we talk about why in mastering query tuning. But if I want to see, just for comparing back and forth, what the logical reads were for queries, index equals 1 always gives you the clustered index, or if there's no clustered index, it reads from the heap. Then I'm going to hint each of the indexes that we created. This was the first index that we created. Then I'm going to hint the one on display name location. Then I'm going to hint the one on location display name. If I compare the number of logical reads that were done by each of them, this one was a table scan. Our first index was 16 logical reads, then the one on display name location, then the one on location display name. Honestly, all three of the bottom ones are pretty good. End users aren't going to complain about the difference between any of the bottom three. It's tempting to take the handcuffs off of SQL Server and let SQL Server choose which one it's going to use. And it's tempting to call that one the best. In this case, SQL Server chooses to use the index on location and display name, but that's not the best. Before you go pick a winner, you want to go look at the number of queries that you're running. Remember earlier we queried for just say display name equals Alex. If we still run that query plus this new one, then I probably need to have an index that leads with the display name, not the one that leads on location. Because if I go back one slide, and I wasn't calling you cousin, I was saying because just because this one picks location first doesn't mean it needs the index sorted by location first. This query would use absolutely the same indexes. So what I want to pick it on is based on whatever columns I query the most overall in my workload. If I still run this query here, then I probably want my index to lead with display name. Now let's start to mix it up a whole lot harder. We're going to use a mix of both equality and inequality searches in our where clause. And when I say inequality, this is what SQL Server terms as inequality. It's not necessarily what you and I would term inequality searches. Greater than or less than, sure, that makes perfect sense. But to SQL Server, is not null is called an equality search. and is null is called an equality search. Seems kind of goofy to me. They both usually involve large numbers of rows, but whatever. If you have an in clause that has exactly one value, SQL Server calls that an equality search. Whereas if you put two or more values in your in clause, then it calls it an inequality search, which is kind of funny. Because if you have an in clause with, say, exactly two values, or three or four, what SQL Server really does is two or three or four index seeks. It seeks on each of the values. You have to have a pretty big amount of matching data, like a pretty big number of ins, before SQL Server will just end up scanning. Most of the time it does seeks. And then finally, like and not like are considered inequality searches, whether you use percent signs or not. Let's start with an inequality search that we can all agree on. Show me all of the Alexes who do not live in Seattle. I'm looking for anyone other than Seattle. Well, think back about how we're going to execute this with the two indexes that we had earlier. We had one index that started with display name. We had another one that started with location. If I use the one that starts with display name, what SQL Server can do is go dive bomb directly into just the Alexes, reading through those, looking at their locations, and returning just the ones who are not in Seattle. We already know that there aren't that many Alexes overall, so it's not like we're going to read a whole ton of data. We are only reading the Alexes here. But the situation is dramatically different when we talk about an index that begins with location. If I use the index that begins with location, I can't seek to Alex. I have no idea where the hell he lives or she lives. It could be in Moscow, Russia. It could be in Atlanta, Georgia. If I'm trying to find all of the Alexes who don't live in Seattle, realistically, you and I would say that we're scanning all of the locations. We have to read London, Albuquerque, Zimbabwe, every single location in the book to find all of these Alexes who don't live in Seattle. But what does it look like to SQL Server when we go look at execution plans? To find out, we're going to use our index hint technique. This looks just like the screen we ran earlier, but what we've done is change the query to filter on anything other than Seattle. And let's look at our number of logical reads. The number of logical reads about 45,000 when we use the clustered index. It's still about 16 when we have to look at all the Alexes regardless of any sorting on location. Look how close those are. Really, our original index that we created first is going to do a really good job here. The locations weren't sorted in order, but if I'm looking for anything but one location, I'm going to read most of them anyway. This one's clearly the loser. If we had an index sorted on location first, we're going to have to read a good chunk of the index in order to find all of the Alexes who do not live in Seattle. To you and I, when we look at these logical read numbers, you and I would call this a seek, and we would call this a scan because we're reading through a good chunk of the data, and you and I would call this a scan because we don't know what location we're jumping to. This is where it starts to suck. If I'm looking at the execution plans, here's the execution plan that leads on display name. Here's the execution plan that leads on location. They look the same. They both look like index seeks. And you might be asking yourself, wait a minute, SQL Server, what the hell location are you seeking to? Because I didn't specify a location. I said anything other than Seattle. And SQL Server says, as a matter of fact, you did specify a location. SQL Server says, what I'm going to do down here when your data is sorted by location is I'm going to seek to Seattle and then read everybody higher. And I'm going to seek to Seattle and I'm going to read everybody lower. That is not what you and I would consider seeking. Another proof of that is if you hover your mouse over each of these index seeks. So I'm going to hover my mouse over this one, hover my mouse over this one. The one on the far left-hand side is when we did the seek on display name, then location. When we did the seek on display name, then location, we didn't have to read that many rows. We only read a small number of rows, a few thousand. But when we had that index on location, then display name, here's where SQL Server says, I'm going to seek to Seattle and read up, and I'm going to seek to Seattle and read down, which is BS. And so as a result, he has to read a huge number of rows. When you have both equality and inequality searches, you might be tempted to think that because we have an equal sign here, we should put this column first in the index. And because we have an inequality search here, that we should put that second in the index. That is not the takeaway. The takeaway is I want to put whatever filter in the query reduces our search space by as much as possible first. If I'm looking, in this case, for equals Alex, and there aren't many Alexes, then I want to put that first. If, on the other hand, there are a ton of Alexes, and my other filter is very selective, then that's the one that I want to put first. When I talk about selectivity, and when you read about selectivity out on the internet, people think that selectivity is about how unique or non-unique the data is. People will look at this and say, well, if you're filtering by tree color, there are only 2 tree colors here. Tree color isn't very selective. Right, that's true if I'm looking for this color. But it's not true if I'm looking for that color over there. If my filter is looking for that color over there, if that's the thing that I'm usually looking for, then this data, the selectivity of color, is amazingly selective. It has nothing to do with the data. It has everything to do with your where clause. For example, the term where display name equals Alex is very selective. Less than 1% of the data matches. If I'm looking for location equals Seattle, that is also beautifully selective. On the other hand, if I'm looking for location anything other than Seattle, that's not very selective at all. Selectivity is all about the contents of your query, not the contents of the data. For example, if I walk into a bar, which sounds kind of good right now, I can't drink when I teach training classes, not because I need to be sober. I think that most of you wouldn't miss if I had a drink or two. It's that it burns out my voice when I drink alcohol, so that would be bad. If people walk into a bar and I ask you, hey, how about the labels on these bottles? How selective are the brand names? You would think that the label on the bottle is extremely selective. But it really all depends on your query. Because if your query says, go show me all the booze where the brand name has an E on it, well, suddenly this isn't selective at all because there are many bottles up here on the rack that have E in the brand name. Selectivity has nothing to do with the contents of the data. Selectivity has everything to do with the contents of the where clause. When you're trying to figure out which column goes first, don't think about the uniqueness of the data. Think about what percentage you actually search for. And the way that I test that out in real life is that when someone hands me a query to tune and it's got multiple things in the where clause, I'll actually tear this out. I'll say, go count the number of rows where this filter matches, then go count the number of rows where this filter matches. Because if you looked at the data in the Stack Overflow database, last access date would appear extremely selective. Everyone logged in at different times. Every value in here pretty much is unique. But if my query looks like this, show me all the people who logged in before right now, well, that's everybody. Until the terminator logs in from the future, every last access date that we're looking for is always in the past. So this isn't selective at all. On the flip side, there are only a relatively limited number of reputation scores out there, certainly not as many unique values as there are for last access date. So you might think that this might be less selective just because there are less distinct values for reputation. But that's not true. Because if our query is filtering for reputation equals 0, odds are almost nobody matches. Because from a business perspective, Stack Overflow gives everyone one reputation point when they create their account. It's hard to go back down to exactly 0 reputation points. Very few people would match this. This makes a much better leading candidate for an index for this query. So to recap what we talked about inside this first module, get it, he's got a cap and then he put another cap on. He recapped. To recap what we talked about inside this module, if you're, I kill me. I've given this presentation before, and this slide always makes me laugh. Anyway, if your queries only have equality searches, then the order that you put them really isn't all that important. Doesn't really matter which one you lead with. The exciting stuff comes in when you have inequality searches inside your query. Then key field order matters a lot. Key field order is all about finding which one reduces your search space as much as possible, as quickly as possible. That's what selectivity is. When you look at the execution plan and you see an index seek, that doesn't mean that you're seeking to a specific row. That just means that you're seeking on the first column in the index, and subsequent columns in the index might actually be scans. When you're choosing the order of columns for an index, generally speaking, columns in the where clause need to go first. And the way that this class works is that I'll start by teaching you a set of good basic rules, but basically in every next module, I'm going to tell you situations that break those rules, because let's face it, we're in the fundamentals. Your career is probably already several years long. You've probably already got situations where it doesn't make sense to put the columns in the where clause first in the index. And we'll talk about when to break those rules in the next module. Generally speaking, selective query filters go first. Selectivity has nothing to do with the contents of the table. It has everything to do with the uniqueness of what you're searching for in your query. Generally speaking, the columns that you filter on most should go first, so that as few indexes as possible can help as many queries as possible. To test it out when you're designing indexes for a query, go write a separate select query for each of the things in the where clause. Count the number of rows that match each of the things inside your where clause. Now, it's time for your first hands-on lab to reinforce what you just learned.